Hello and welcome everyone to the last day of summer camp on citizen science and astronomy. Our session highlights are Globe at Night, a citizen science project to quantify light pollution and UV spectral analysis of Jupiter. So, to start with today's session, we have Ravina Hemraj Paldiya. She is an MSc student at IITM. So, without further ado, I request her to begin with today's session.
Hello, am I audible?
Yes, loud and clear.
Okay, yes. So hello everyone. My PPT is visible to everyone.
Yes, it is visible.
Okay. Okay. So topic for my today's talk is a planet in ultraviolet wavelength. So in first section, I will explain. I will give information about the Jupiter planet and which satellite data I have used for the further analysis. And in second section, I will analyze this Jupiter's data from IOE archive. So some facts about the Jupiter. As we all know that Jupiter is the fifth planet from the Sun, and it is the largest planet in our solar system, with a diameter is about 11 times the diameter of Earth. It has a mass approximately 318 times that of the Earth. Jupiter's atmosphere is primarily composed of hydrogen, which is about 90%, and helium is about 10%, and other little amount of gases like methane, ammonia, and water vapor. And this Jupiter is famous for its great red spot and massive storm that is larger than the Earth and has been raging for at least 400 years. Jupiter has the strongest magnetic field of any planet in the solar system, which is about 20,000 times stronger than the Earth magnetic field. And Jupiter has 79 moons, and it has a faint ring system which is composed mainly of particles ejected from its moon. And Jupiter has the fastest rotation rate of all the planets, completing one rotation in just 10 hours. This rapid rotation causes a noticeable bulge at its equator, and the temperature of it and temperature at the cloud top of the Jupiter is about 145 degrees Celsius. But it gets much hotter towards the center. And we can see the great red spot is around here. Okay, so this is the image of Jupiter at visible wavelength, and this is at ultraviolet wavelength. We all know that visible wavelength lies from 400 nanometer to 700 nanometer, and ultraviolet wavelength is from 100 nanometer to 400 nanometer. So we can say that UV light is more energetic than visible light. These are the some images of the other planets in UV light. This is image of Sun, Mars, and this is UV image of Saturn. Okay. So actually, why we are studying celestial objects in ultraviolet light? So first reason is hot and energetic processes. Like stars, particularly young and hot star, emit a significant portion of their energy in ultraviolet spectrum. And another reason is different elements and molecules absorb and emit ultraviolet light at specific wavelength. So, by analyzing the UV spectra of an object, we can identify the element and molecules present, revealing the object's chemical makeup. And the third reason is invisible details revealed. Dust and gas clouds can often obscure our view of object in visible light. So, however, some dust become transparent in UV light. So, allowing us to see through these clouds and peer into hidden regions behind them. So, this is crucial for studying star formation regions or the cores of galaxies. And the another reason is comparative studies. So observing an object in both both visible and UV light allow us to see a more complete picture. Differences in how an object appears in these two wavelengths can reveal important information about its temperature, structure, and ongoing processes. So this is the comet Shoemaker-Levy 9. Uh, this comet Shoemaker-Levy 9 was discovered by a team of astronomers included Eugene and Caroline Shoemaker and David Levy in 1993. So this comet because of Jupiter's extreme strong gravity, this comet break into multiple fragments. These fragments remain gravitationally bound to Jupiter, forming a new and broken up orbit around the gas giant. So this new orbit, however, it was unstable, and it was only a matter of time before the fragments collided with Jupiter. So this impact began on July 16, 1994, and continued for 6 days. The fragments collided into Jupiter's atmosphere at a speed of about 60 kilometers per second, releasing an enormous amount of energy. Each impact created a giant fireball and a dark plum of debris that rose thousands of kilometers into Jupiter's atmosphere. The impacts left behind massive scars on Jupiter's atmosphere. These scars appear as dark ring features, with the central dark spot being the hottest area of the impact. The surrounded rings were formed by the ejected material from the impact. These scars left behind, the scars which are left behind were not permanent. They were significantly enough to observe for months by astronomers around the world. Uh, this is the comet Shoemaker-Levy 9, and we can see the scars here. Okay, so yeah, this is IUE. IUE is International Ultraviolet Explorer Satellite. This satellite is basically designed to observe a celestial objects in ultraviolet range, and it is a collaborative project between NASA, ESA, and UK. So, in my further analysis, I will take the data from this IUE archive. Okay, so these two are the spectra of Jupiter. This spectra of Jupiter is before the collision with comet, and this spectra is after the collision with comet. So we can see that after the collision, the energy flux is very high. Okay, so now in analysis, I will use this spectra to do the analysis. So first, I will show you that how to download the IOE data. So first, search IOE archive. Okay. So go to data search and search for. So here we can download the data of Earth, Moon, planet, and some active galaxies and many more. So now we are going to analyze Jupiter's data. So planet, search. Okay. Okay. So here we can find in every data of planets. Okay. Okay. These are the Jupiter's data. To download it, just go click this link and we can download this data. So I have already downloaded the data of Jupiter. So now I'll do analysis part. This is Linux terminal. This terminal is visible to everyone.
Yes, yes, the terminal is visible.
Okay. Okay. So my data of Jupiter is this. This data is in zip file. So first we need to unzip it. So the command to unzip it is gunzip and this file name. So yeah, now it is in text format. To rename this file, just use the command mv, copy this file, Okay, yeah. So this is in text format. To see the data, just use command more and this data. Hmm. So this is the information about the data, what is exposure time and when the observation began. And in this first column, it is wavelength. In second column, it is flux, and in third column, it is error in the flux. Okay, we will do this analysis in HiaSoft. So, but HiaSoft cannot recognize these lines. So first we need to remove these lines. So we will make another file in which only data will be there. So the command for that is okay, tail minus 9n plus 19 means number of lines. So these lines are 19. Uh, okay. Okay, yeah. So we made this another file. In this file, there the lines will be no lines will be there. So to see more, okay. So yeah, there is no lines, flux, wavelength, flux, and error in the flux. Uh, okay. So actually in HiaSoft, we need range of wavelength. See, in this file, there is only wavelength. So for range of wavelength, we need to make another file. So the command for that is awk print column 1 minus 1.33. 1.33 is the resolution. Means dif, means dif, this, take take difference between any these two wavelength and divide it by 2. So that will be resolution. And this is called column 2. Okay. Okay, so we make new file, this calibrated file. In this, there will be range of wavelength. To see the data, just write more and this file name. Okay. So yeah, this is minimum wavelength, this is maximum wavelength, this is flux, and this is error in the flux. So yeah, in HiaSoft, there is particular package which is known as Xspec, which takes the spectra and do the analysis of it using some models. So these all files, we can see these all files are in text format. Okay, but Xspec cannot read this format. So it needs some format like .pha and .rsp. So we have to make these two format. So the command to do that is flx2xsp. In file is input file. We will take this calibrated file. PHA file is the extension should be .pha. RSP file is okay. Here also the extension should be RSP. X unit is Armstrong. Y unit is unit of flux, which is Ux per centimeter square. Okay. Just be careful while writing the units because it should be small s only. Because if you write capital S, then it will show error. So yeah, this .pha and .rsp files are there. So now we can do further analysis. So now go in Xspec, load this pha file, data, and this pha file. Okay. So to see this data in plot, the command is cpd/xw. So now we can see this another window, pgplot window. PL means plot and LD means log. So we will plotting our data in log scale. Okay. So in this area, we can see the error bars of this data are very large. So we need to remove this. We need to ignore these channels. So the command for this is ig. Ig means ignore. So this we need to ignore till 180 channel minus 180. So yeah, we can see channel from 1 to 180 ignored in the spectrum. So then plot. So yeah, now we can see a good spectra. So this spectra is in channel space. To go in energy space, we just have to write the command set plot. En means energy plot. We can see this spectra in energy space. Okay. So from this we can see the every spectra consists of three components: continuum, emission lines, and absorptions line. So this is continuum. These are some emission lines and these are absorption lines. Okay. So first we will model this continuum spectra and then lines. To model this continuum spectra, we use model power law. MO means model and model power law. Okay. So to model this continuum spectra, we use model power law. Photo index. So yeah, power law has two components. One is photo index. Photo index means slope of the curve. So typically we take this value approximately 2. And another component is normalization. And normalization means area under the curve, which is 1. So these are the values which we have given. Now fit these parameters. Just enter. Okay, plot. So yeah, this is a power law model. We can see the lines which are above the power law. These are the emission lines and the below ones are absorption lines. So to fit these emission lines, we use model Lorentzian, and to fit these absorption lines, we use the model Gaps model. So okay, so in this another plot, this is residual plot. So try to bring all these data points near the zero line. Because if your error bars fall on the zero line, that means your model is consistent with the data. So now we will first we will fit these absorption lines. So for this we will need energy value. To see from this to get energy value is kind of difficult. So we will go in IPL. IPL is interactive plot. IPL is interactive plot. Okay. So yeah, now we are in another plot which is PLT. Previously we were in XSpec. So right cursor Put your cursor around here. Okay. We got these two values. This first value is x-axis value, means energy value, and this another is y-axis value, means counts. So yeah, add C1 gaps. Gaps is model which is used to fit these absorption lines. Add C means component. Now we have to add this gaps model to first component. First component is our power law. So yeah, so this power law. This gaps model have three components. First is line energy. That means what is the energy? What is the energy of that line? Which we just find out this. Just copy this value, comma 0. That means we are going to freeze this parameter. And another parameter is sigma. Sigma means what is the width of this line? Means what is the width of this line? Which is approximately 1 e to the power minus 0.5. And another component is strength, which means the depth of this line. What is the depth of this line that this parameter shows? This is again 10 to the power minus 5. Now fit this parameter plot. Okay. Okay, so this line is fitted by this model. So now we will freeze this two component. 2 to 3. Okay, so sure. So why we are freezing this parameter? Let's say if we model this another line, then after modeling this, the values of this previous model will not change if we freeze these parameters. If we don't freeze, then maybe it width or line energy may be changed. So we need to freeze this parameter. So now model this, fit this another absorption line with the same command. Just go in IPL, cursor, take this energy value. Okay, so we have to add this model to the power law. Now power law is shifted to second component. So add C2, 2 means second, gaps. So now we are adding this gaps model to second component, which is power law. So again, line energy is this. Sigma is again 10 times smaller than this line energy. Strength is again the same. Okay, so this another line is also fitted. So we'll freeze these parameters also. 5, 6. Okay. Yeah. Now we will fit these emission lines. So again, take the energy value. Three. Now we will use model Lorentzian. Now and this power law is shifted to third component. So that's why we write here 3. Yeah. So Lorentzian also have 3 component. First component is line energy. So just copy this value here. Means we are freezing this parameter, comma 0 means width Again, second parameter is width. Width is again what is the width of this emission line. Approximately it is 10 times smaller than the line energy. So we can write 0.4. Normalization, and it is approximate 1. Okay, so this line is fitted. Now we will again we will freeze these parameters. Eight to 9. Okay. So there is one more absorption line and some are emission lines and absorption lines. So quickly we will do that also. Just take first energy value. Put your cursor here. So this is energy value and this is count rate. We are adding gaps model. Line energy is this. Sigma is again 10 to the power 5 times smaller than the line energy. One. Strength is again the same. Okay, so this absorption line is also got fitted. So again, so we have to fit this line and this line also. First freeze this parameter. 11, 12. To see that frozen parameter, just write the command show. Okay. So now we are going to fit this emission line. Cursor. Okay. Add C5. 5 because power law is now fifth component. Width is again 10 times smaller than the line energy. So we can just round off this energy value. 4 exponential. Normalization is again we can take 1. Fit. Okay. So now we will fit this absorption line. See, the lines which are above this power law is emission lines and below ones are absorption lines. So IPL cursor. Add C 6. Now power law is in 6th position. Gaps. Sigma is again the same value. This is also. Okay. So freeze this component now. Till 17. Okay, so this is again absorption. So this is last one. So now we are fit this. At C7. Sorry, gaps. So line energy is this value. Sigma is -5, exponential -5. This is again the same value. Okay. So we can fit one Lorentzian here also. So just do that. Cursor. Put your cursor somewhere here. At C8 power law. Oh, sorry, not power law. It will be Lorentzian. Sorry. Okay. So to delete any model, you just have to type del C, means delete the component. This 9, this 8 component. Okay. So again, take this value. Add C8 Lorentzian. Width is again 10 times smaller than this energy. So 4 exponential minus 0.4. Okay. So now throw all these parameter. Throw means unfreeze it. 1 to 26. Fit and plot. Okay. So this is the final spectra which is fitted by these models. To see this model, just type this plot EUF spec. Ideal range Y. Okay. So now we can see all these models. This Lorentzian model, these absorptions, these are Lorentzian. So we can see every model through this command. So this is how we will perform the UV spectral analysis. Okay, so by doing this UV analysis, we can find the physical information about the planet, like what is the flux value of that planet, width and energy of the emission lines and absorption lines. To find out which elements are there in absorption, just go in Google. Okay, okay. So let's say we have to find which elements are there for absorption. So go in this link, plot of small aperture asked date. So these are absorption lines. On this, yes, we can see for this line the aluminum element will be there. Chromium is for this, and for this range of wavelength, the iron, this element will be there in Jupiter's atmosphere. Okay, this is magnesium. So okay, so this magnesium element is for absorption lines. This is manganese. Sodium is for this emission line. Here all elements are there. This is for zinc. So we can see. This prominent absorption in Jupiter's atmosphere is happened because of this magnesium element. Okay. So yeah, this is my talk on how to analyze the any spectra. So by analyzing this spectra, we can find any physical information about this. So thank you so much.
Thank you for this wonderful presentation. Now, if anybody is having any questions regarding the presentation, please ask now. Yes, please open your mic and ask your question.
I have a doubt
Yes.
um about determining it. What like from which app do we do it to determine the planets, like the model of the planets?
From which archive?
Yes.
This is IU archive. I show you na. Go in Google, type IU archive. Then this must IU archive. Just you have to go in this link, this data and retrieval, this form, search form. And if you want to download their data for planet, then go in this move for moon, this Earth for this. So now we are doing for Jupiter's planet. So we'll go in this for this planet, and then search. So here so data of all the planets, Mars, Uranus, Neptune. So if you want to download the data of Neptune, then just click on this link, LWP 16149. So this is bad data actually. So this is data of this Neptune. So to download, just ask a table of large aperture fluxes and wavelengths. Just click on this link and you will download this data. Okay. Is that clear?
Yes. Thank
Okay.
you.
Um,
Anybody having any other queries, please ask. I don't think there are any other questions.
okay.
Thank you for the presentation once again. I think we can now move on to.
Thank you, sir. Thank you.
Thank you. Our next speaker for today is Dr. Mila Mitra. She is the co-founder and academic head at Space and STEM. Now, I would request her to start with her presentation.
Yeah. Hello, everyone. Thank you, Hexstar Universe and SS Citizen Science for inviting me today. And I'm very happy to share. I'm going to talk about a couple of different citizen science projects, and I hope students would be interested in joining those. So Ravina talked about I'm going to talk about something first that is, very fun and really So I hope you can,
Yes, ma'am. Visible.
you can see it. Okay. So like I said, I'm going to be talking about two projects, and hopefully in this amount of time I can give you a glimpse into both of them, and you can follow it up further. So I'm going to be first talking about Globe at Night, which is a project to preserve our starry skies. So let's understand what that means. This is a project by Aura and NOAO, which are international organizations that are international astronomy organizations, and it is by Neuer Labs. One second. Yeah. Okay. So, Globe at Night is an international citizen science project, and the whole goal of the project is to make people around the world aware of the impact of light pollution. So, what is light pollution? Why is it particularly, a problem or of interest to people who are astronomers or people studying space? And also, how do we evaluate light pollution in our locations to create a global map? So so I'm going to describe further what you do in this project. It's called globeatnight.org, and later on I am going to lead you to the website and tell you exactly how to do it. So it is to raise awareness of the impact of light pollution. And how do we report what the light pollution is? We correlate it to observing specific constellations. So there are easy steps in this project. Everybody around the world observes the same constellation, or rather divided by Northern Hemisphere and Southern Hemisphere. Then you count how many stars you can see in the constellation, and this is correlated to light pollution in your area. And then you have to report it along with location information. Okay, so first let's go to what is light pollution. I think the audience here today, probably knows, everybody knows this, but sometimes you talk to people outside the astronomy interest group, and they may not know what is light pollution. We do know what is air pollution, what is noise pollution, what is water pollution. So similarly, there's a concept called light pollution. Look at this picture. It's of New York City. It's so beautiful, but however, so much light is a problem for us. So light pollution is too much light. So how does it affect? It affects the usage of energy. And of course, now that saving energy is a very important thing, it definitely affects astronomical research, because most observers and most astrophotographers are looking for dark skies to photograph, and the amount of ambient light you see can really cause a problem for what you're trying to photograph or trying to observe. And of course, now with so many constellations of satellites, that itself is also creating these same kind of problems. Now, light pollution also affects human health. Too much light affects mental health, causes stress, affects sleep patterns, and so on. Similarly, wildlife are also disturbed by too much light. Sometimes their migratory patterns are disturbed, sometimes their sleep patterns are disturbed. So we do need to be aware of light pollution from different points of view. Here are some types of light pollution. Glare, these are the words that are buzzwords that are used in this kind of topic. So glare is very bright lights from a focused source, such as headlights of cars. Then the sky glow, which is ambient light over a city. Light trespass is where you have a light for a specific area. So say, for instance, your garden, but it actually trespasses into neighbors' areas or neighbors' windows, and that can create problems for them. overlighting. Of course, we know this problem of malls, of shopping areas, even of offices. They keep the lights on, too many lights on, and it may look good, but it may cause a lot of extra light that we don't want. So we need to be aware that we need to conserve the outside lights. So light what you need when you need it. For example, use motion lights, no brighter than necessary. We do recognize that their lights are needed even at night for safety, for things like that. But we need to be aware of these points. They should be shielded to point downwards. So outdoor lights can have low glare and motion sensors. And of course, we already know for energy saving, we have started using CFL and LED lights. So light pollution and astronomy. So light pollution affects the way we see the stars. We all know that this is a picture of, contrasting the amount of ambient light and what we can see. So here's a picture of the sky with different levels of light pollution. You can see on the right, all the way on the right, how much more you can see when it's a dark sky sight. And again, most of you here, being in the astronomy domain, might know how the scaling is measured. What is the terminology for it? It is called the bottle scale. Okay, so the bottle scale goes from 1 to 9, and it defines the amount of how dark your sky is. Okay, so bottle sky 1 is a very dark area sky, and you can see a lot of stars. And going towards the right, as you get into suburban and eventually urban skies, then you see you get more and more light pollution, and you see very few stars as you head towards bottle sky scale levels 7, 8, and 9. Now, I've said that we are going to measure light pollution. See, all of us attending here today are probably from different parts of India, and maybe some from different parts of the world. So we all have different light pollution. I'm sitting and speaking here from Delhi, which is one of the worst. But some of you might be better off, or some of you may not be. So how do we quantify it? We quantify it by measuring the faintest stars you can see. Okay, so that is the limiting factor to telling you how much light pollution is there in your area. Okay, so that word is called limiting magnitude. So what is the faintest stars you can see? That is called the limiting magnitude. So I'm going to give you an example. For example, this is Orion, which all of us know how to spot, mainly through the 3 belt stars. Orion has some bright stars and some fainter stars. Now, this is Orion under different skies. This is a bottle level 9 sky. So it's a little confusing. So if your light pollution is high, then you see only the brightest stars. Okay, so here, inner city skies with high light pollution, you only see the brightest stars of Orion. As I flip through and the light pollution gets less, you start seeing fainter stars. Okay, so bottle level 5, and now you see bottle level 3 in rural skies. You see much fainter stars in Orion and also all around it. So bottle level 1, which is the excellent dark sky site, you see all the stars of Orion and all the stars around it. So again, the concept is, if you don't know magnitude, let me just define it for you. Magnitude is the brightness of a star. Now, we do recognize that stars are of different sizes and there are different distances. So the concept used is apparent magnitude, which means how bright does a star appear to you here on Earth. Now, apparent magnitude is a scale. However, it's a reverse scale. So just keep that in mind. It's a reverse scale where the brightest objects are less in number or negative even. Okay, so the brighter the object, the lower the number. It's a reverse scale, inverse scale. So here on this scale, for example, the sun is at minus 27 or so. The full moon is at minus 12. Of course, those are the brightest objects we can see. Then Venus is at about minus 4. So these are negative numbers. Sirius is also a negative number. Okay, and then we go on to Polaris. And now the naked eye limit that we can see with our eyes is about 6. So remember again, we are going to positive side, means they've got very faint. So naked eye limit is about 6. And Hubble Space Telescope can see at about 28. So this gives you an idea of how the magnitudes are. And now we are going to identify. So if we look at a constellation, suppose we're all looking at Orion. Again, I'm taking this example because it's easy to spot. Then I've shown an image which marks out what are the magnitudes, apparent magnitudes of some of the stars. So we have the brightest stars, which are Betelgeuse or Betelgeuse, Rigel. These are 0 point something. Okay, so they're 0 point something. Then we have some that are 1 point something. They're less bright, but still very bright in the scale. And then there are some that are in the scale, magnitude scale of 2. Okay, so when you go to Globe at night, I'll show you how to go there. They have something called magnitude charts. So you don't have to know it in your head. You can compare these charts. You can look up, compare the chart, and see what does the sky look like above you. So in the magnitude chart of Orion with magnitude 0, you can only see the very brightest star, which is Rigel. So if you only see one star, then your limiting magnitude is 0, because that is the faintest star you could see, which in fact is the brightest star of Orion. As you get, maybe you get to a place which is a little better, and your limiting magnitude is 1. So if you look up, and you can actually see Betelgeuse, Rigel, Procyon, and so on. You don't exactly have to know it. You can compare this map to the Orion that you see. Then you would pick magnitude 1. So which means the faintest stars you see are magnitude 1. And so on. In this location, the faintest magnitude you can see is magnitude 2. And again, remember, don't get confused. The faintest magnitude, the number is getting higher because remember that magnitude is an inverse scale. So in this one, this location, you can see stars of magnitude 2, which are all the bright stars of Orion, and magnitude 3, and so on. Okay, so finally, if you're in a very dark sky area, you would see something like this, which is magnitude 7. So these magnitude charts are given in the website, and that is what you would be doing. You would be looking at a constellation and trying to see which of these magnitude charts best match what you are seeing in your night sky. Okay, so again, what do you do in this project? You observe a specific constellation and find the faintest stars. And don't get confused at brightest stars and faintest stars. Everybody can see the brightest stars, but what is the faintest star you can see in the constellation determines your level of light pollution. Okay, so the way the campaign works, they have campaigns every month, and the campaign runs for a week or so. And every time there's a different constellation. How is the constellation picked? It's picked by something that's probably overhead between 8 and 9 p.m. So it's a convenient time. And, so I've given you the chart of which are the constellations. And sorry, I didn't, they have the same, they have a list of constellations in the Southern Hemisphere too, but I've only copied and pasted here the ones visible from the Northern Hemisphere. Okay, so Northern Hemisphere we are just finishing up June. So if you look at the second one, which is 26th June to 5th July, the constellation is Hercules. Now, Hercules is a little difficult to spot, and it is near Vega, the bright star Vega. and you would have to look it up using an app. But some months are a lot better. For example, even in the next one I show, from 26th July to 4th August, you can also observe Cygnus, which is much easier to spot. It's Cygnus the Swan. It's pretty easy to spot. So you can wait, you can try it out, and you can wait till you find later on in the year, when you find a constellation that's easier to spot. And of course, in winter, they do have a choice of Orion and Leo and things like that. Okay, so I'm going to show you this slide here and then go to the website. So there are 6 easy star hunting steps. That is the app called app.globeatnight.org. I mean, I want to warn you that the word says app, but it's not really an app. It just type it in your phone on the web browser, and that's how you should do it. Okay, just type in the word app.globeatnight.org. You would go outside at night after 8 p.m. and they do select these campaign dates based on the fact that there would be no moon, or the moon would be less. Adjust your eyes for 10 minutes, because that's when your eyes can start seeing better. It takes a few minutes for the eyes to adjust to the dark. Then find the constellation using an app. And again, I've given the example of Leo here, but this month it is Hercules, and next month it is Hercules and Cygnus. So on the phone, you would go to the Globe at Night report page, and I'm going to show you this page on the website right now. But you would do it on the phone, so you can take your phone outside and be ready to report. So on the phone, there is a icon on the top that lets you tick it, and that puts you in nighttime mode, which means the lettering becomes in red. So you'd have to enter date, time, and location. Of course, most of us have smartphones, and all these are automatically entered. The date, time, and your location is automatically entered. Then you have to match the star chart. So this is where you would look up at the constellation that everybody is watching and compare it to the magnitude charts and select the magnitude chart that it resembles the best. You also have to give some local information, like describing the cloud cover and some other local circumstances, like do you have a street light nearby? Do you have an office or a mall nearby? So you have to just tick on a few of these things and then submit the data. Okay, so you can do multiple submissions. They just go in. So the app, again, on your phone, tries to get this information. When did you make your observation? Where did you make it? How dark is the sky? What are the sky conditions? And then send in the data. Okay, so I'm just going to stop sharing and go to the website. Okay, so this is the Globe at Night website. Okay, so when you come in this home, you can learn about different things, like under the learn, you can go to constellations, light pollutions, and so on. You can observe. If you go under observe, then it gives you what are the campaigns ongoing or which are the campaigns coming up. Okay, so here they have a list of northern constellations and southern constellations through all of 2024. So right now, like I said, we have a campaign coming up at the end of June, and then again at the end of July, and that is Hercules and Cygnus. And in August, again, it is Cygnus. And in September, it is Cygnus and Pegasus, and so on. It moves through to try to highlight a constellation that is easily observable. Okay, So that's what you have under observe. And here you also have magnitude charts. So this is just to explain it to you. What are the magnitude charts? Okay, so you can, it's automatically selected Bootes, which is the current constellation. So you can select something else if you want. For example, I said Hercules is coming up. You can change it to the latitude that you are in, and it's going to show you how the magnitude charts are, like what you can see in Hercules. Like I said, it's near Vega. Do use that. Vega and Arcturus are both not hard to spot, so do use those as a reference to find Hercules. And you can see what they are like in magnitude 0, which is a very urban sky with a lot of light pollution. You only see Vega, and not Vega and Arcturus, and nothing really of Hercules. And magnitude 1 and 2, 3, you start seeing more objects. Okay, so you're going to have to match these sky charts. So let me show you how to report this. You go to the option called report, and like I said, you will be opening this on your phone. You can play with it now, and like it says, it wants to know your location because it automatically pre-fills it. Now again, uh, you can play with it on your laptop, but do type this in or type in globe at night on your phone, and then go with it outside and do this whole thing on your phone. Okay, so that's how you would do it. But if I show you here, then, and like I said, there's a icon on top with the moon, which makes it a friendly to the night sky. So if you're outside, it's going to be in red lettering and not create extra light pollution for you. Okay, so you just have to type in when did you make your observation, where did you make it, and all of this will be typed in automatically. So in the location comments, do put in something like, was it rural, urban, number of street lights. So for example, I can say street light close by, or you can just say urban sky. Okay, so now, uh, did you use a sky quality meter? And I'm not showing you that step, but there are separate sky quality meters that you can find as apps. And those also tell you what the reading is of the dark sky. So you can, if you have that, you can type in the number. And how dark was the night sky? This is where you would look up and try to match which is the constellation, which is the magnitude chart that best resembles what you saw. If you didn't see anything, then you probably are magnitude 0 and you just saw the brightest star, which is Arcturus. Right now, this is Vega. Okay, so you just go and select the one you saw. And of course, like I showed you next in the next campaign, there are 2 constellations. So pick the one you are reporting. And then you say, what were the sky conditions like that night? You can say if it was cloudy. And you can say a little bit more if you have a comment, for example, haze. And then you just submit the data from here. If you have a size starter account, which many of you do, then please enter that email and you get some credits there. Okay, so this is how this Globe at Night project works. So again, like I said, you do this on your phone, although it's called an app, and you just go to Globe at Night, click on report. So I'm going back to Globe at Night. Just click on report, and under report, you'll already get to where you have to report from. I'll show you a little bit more here. They have maps and data which show you what kind of reporting has been done over the years. So if you're interested in looking up light pollution or publishing something about it, then you can you can download data of light pollution over the years. So 2023 they had 22,000 light pollution observations were submitted all over the world, and you can look at these further by downloading data, or you can click on it, and it's color coded so that different magnitudes are color coded from yellow to red. So it's still loading. But yeah, so you can see where it was limiting magnitude 0, where it was limiting magnitude 6, and so on. This will help you, and this helps people who work with dark skies to get an idea of which locations are really good dark skies. Okay, so I'm going to again share something more, which is just a second. I'm alternating different between different applications. Okay, so again, I'm going to conclude this topic pretty soon and just briefly describe the next topic. So, okay, so we've hopefully all figured out what is light pollution, what is limiting magnitude, and how to do this project. Just to conclude it, so there are some softwares and apps that help you find the constellations, such as Stellarium or Stellarium Plus on your phone, then Sky Safari, Star Walk, and then there's a bottle sky demo that I took some of these pictures of Orion from, which shows you how just a very few specific constellations look in different bottle skies. Okay, so now there are some light pollution interactive maps you can find, and see what happens as I go from, I'm going backwards, starting from 2012 to 2018 to 2023. See how much more there is light pollution all over the world, and therefore we do need to be conscious about it. Okay, so Globe at Night, again, there are different campaigns, January, I mean, all the way from January to end of December. So the campaigns are a week or 9 days long and based around when you see less moonlight. Okay, so globeatnight.org, and I hope you all kind of got this. So let me stop sharing and let me take you, I don't know if I should take questions now or at the end, but let me briefly mention the second project I'm going to talk about, which is called RAD at Home. And I am just going to talk about it, but I have not performed this project myself. I have just attended the meetings for it. So, I'm just going to give you a broad idea. Okay, so RAD at Home is really doing radio astronomy at home, or basically it means the concept is that anybody can do astronomy from home. Okay, so RAD at Home, this is the website. Again, don't get confused, I'm talking about a completely different project now. I just concluded speaking about Globe at Night and light pollution. Now I'm discussing a second citizen science project, and many of you know RAD at Home. It's one of India's first citizen science projects. Okay, so RAD at Home mostly uses GMRT data. So GMRT is Giant Meter Wave Radio Telescope, India's largest radio telescope located near Pune. And basically it was started in 2013 by Dr. Ananda Hota. He is the director. He's the one who runs this program. Now, this is basically, it has been established. It gets very basic funding. It's established as a platform where anyone who's a BE or BSc can participate. So this is a concept where they're trying to gather a large group of students who are trained to do serious multi-wavelength astronomy research. But you can sit at home because this project enables you to look at radio astronomy data as well as other data while just getting it online. So basically it's multi-wavelength extragalactic astronomy research. So this project is trying to gather together and create a network of STEM graduate and undergraduate students. And the goal is that someday we are going to come to the big data problem, which is there will be a large amount of data from GMRT and also mega telescope projects like SKA, which I've listed below, is the Square Kilometer Array. It's an intergovernmental radio telescope being built in Australia, and also the TMT, which is the 30-meter telescope to be built in Hawaii. Now, these are all intergovernmental, which means that countries will collaborate. There will be a lot of data, but that is why scientists are needed, because it's hard to look at so much data and not only look at them, but intercompare the data. So how this project works right at home is currently you look at GMRT data and correlate what you see to other freely archival data in infrared, optical, and UV, because as we just heard, even from the previous talk, and as we know, galaxies or other areas look very different in radio astronomy compared to infrared, optical, and UV, because they all highlight different features and different processes going on in that celestial object. So in this project, you learn about something, you work with something called uh, RGB Maker. Okay, so again, RGB Maker is the tool that they teach you how to use. So in this project, you'll have to join and you get trained on how to do it. And you get trained by learning how to use RGB Maker, which is a Python-based tool which helps you look at astronomy data from different platforms. So this is, for example, data in radio, and you in this project you correlate that to different wavelengths, and through that you try to figure out where is the core of the object, how it is spreading out, and so on. Okay, so that is how it works. So you can all join this project. uh, you do get a qualification and you get certified. What they call it is RGB qualified, and they often hold discovery camps at different locations that are often at universities or planetariums or science centers. So if you can attend one of those with Dr. Anand Hota himself, then please do go, and he'll tell you how to do it and you get certified. And then you can join. They keep discussing it on a Facebook group, which is looking at different objects and trying to discuss what you are seeing. So and some of the people who have been working actively on this have submitted proposals and have published papers. So it's a great way for you to be involved in very good science. So rad at home, how to join discovery camps are at different locations, or join the Facebook group that I've listed here. Follow the post and you will be guided how to make RGB images. So, or contact Dr. Ananda Hota, but this is basically how it works. Okay, so this is RAD at home. It's a very good project for BSc and BTech people. You'll be looking at different celestial objects. Okay, so with that, um, I have described the two projects, Globe at Night and RAD at home, and I will be taking questions. So before I do that, I would just like to introduce myself, Dr. Mila Mitra. I am from STEM and Space, as Hexstar introduced me. And we ourselves, STEM and Space does a lot of projects for kids from schools mostly. And we are doing a 5-day summer camp coming up next week, 10th to 14th June, which is tomorrow, and again 17th to 21st June. And we have summer camps for grades 3 to 8. And these are all hands-on, and we give you the kits that you would be working with. So if anybody is interested in this, do copy the number, or you can contact me. Yeah, so I'll just leave it on for a second. You can contact us. And with that, thank you, everyone. And I will take any questions now. I hope that was not too much to process. I did talk about two different projects. So especially if you have any questions about Globe at Night, let's take that first. Anybody would like to ask anything? Okay, so I'm mostly done with this talk then. So
If
thank you.
anybody is having any queries, please ask right now.
Okay, so feel free to ask questions later. Many of you are in the citizen science group, so you do reach out and talk to us if you want to. So yes, Globe at Night is a fun project. You can do it, and Rad at Home is a more technical project, and you can get certified for Rad at Home. Thank you, everyone, for joining today.
Thank you, ma'am, for the wonderful presentation. And thank you to all the participants who have taken the time and joined the session. Thank you. Have a nice day.